Let's talk about RAID. RAID, R-A-I-D, stands for Redundant Array of Independent Disks. So the first thing is we're going to talk about multiple disks that are each independent from one another being used together as a redundant array. The key word here is redundant. And why would we want to do this? There are three main reasons that we would want to employ independent disks together and turn them into an array. The first, very obviously, is size. That's reason one. If we have need to store more data than a single disk can hold, then somehow we need to combine disks together to have greater size. The second is performance. Perhaps we need a storage solution that provides better performance in terms of total throughput in reads and writes. In other words, we can read or write more megabytes per second than we can do with a single disk. So we will combine them in such a way that we gain some advantage by being able to use multiple drives in parallel. And the third rationale, which is the one that is most commonly discussed with respect to RAID probably, is reliability. Reliability. This is where the redundancy comes in. By redundant, what we mean is we have more drives than we actually need to hold the data. And the reason we would have more drives is so that we can put redundant information onto the array, so that if we were to lose the capability of one of the drives, if the drive were to fail, we still have the data available. We can still recover the data and indeed can even continue operating the array even with a failed drive. So we'll talk quite a bit about reliability. And there are various synonyms here. I have said reliability, but there are various other words that could be used in place of reliability. For example, we could talk about fault tolerance, meaning we want to be able to tolerate a fault or a failure, right? Redundancy. The information is stored more than once. It is redundant, and that makes the array more reliable. Okay, more on that as we go. So let's talk about the RAID levels. And there are many different RAID levels that we will not discuss today. I'm going to discuss the most common ones and a few hybrids so that you have an idea. But I'm going to start with one that really properly shouldn't even be called RAID. And that is actually called RAID level 0 or RAID 0. Now, why do I say that it shouldn't be even really properly called RAID? Because remember, the R in RAID stands for redundant, meaning that there's some redundancy of the information. But in RAID 0, not so much. We actually don't have any redundancy in RAID 0. Okay, as we start to talk about the RAID levels, we need some data so that we can provide some examples. We need a concept of data that we want to store so we can see how it's divided across the disks. So let's do it this way. In a typical hard disk drive, you will have a block size, often 4 kilobytes, right? That's 4,096 bytes. How many bits is that? Well, you multiply times 8, right? What do you get? I think it's 32,768 bits. So that's a typical block. And in all of the RAID levels we're going to look at today, when we're splitting data across disks for performance or for redundancy, we're going to be working with them a block at a time. And so you would consider that your data is split up in 4 kilobyte blocks. But it's very inconvenient for us to show examples using such large blocks. So while a typical block might really be 32,768 bits, we will consider a much smaller block size just for illustration purposes, but understand that it's only for the purpose of illustration. No one uses a block size of this size. We'll make our block size, for the sake of illustration only, 4 bits. Okay? And so we will look at how, if we had such a tiny block size, how the data would be spread across multiple disks. Let's do it this way. Let's say we'll come up with some values. A could be 0101, and we'll say B is 0110, and C is 1001, and D is 1111. Why those values? I don't know. I just came up with them. So we can use a symbol, or we can use the bits to show how the data is spread across the disks. So what are we doing in RAID 0? We have a file which is A, B, C, D. And we're going to divide it up blockwise. Remember, we have 4-bit blocks in our illustration. We're going to divide it up blockwise across more than one disk for RAID 0. So here's what RAID 0 looks like. We've got disk 1 and disk 2. And what we will do is we will write A on disk 1, and B on disk 2, C on disk 1, and D on disk 2. So this is RAID 0 with 2 disks. Okay? So I've taken my file, and block by block I have divided between the 2 disks. First disk 1, then disk 2, then disk 1, then disk 2. Okay? Now, it doesn't only have to be 2 disks. I could have disk 1, disk 2, and disk 3 in a RAID 0 array, and I would store A here, and B here, and C here, and then D would go back here. And so if I have a very large file, then it keeps going. Okay? So all of my data, 4 bits at a time, for all 16 bits of my data have been stored on disks 1, 2, and 3, or in the first example, disk 1 and disk 2. So this is RAID 0. What advantage does this give to me? Well, the first thing, let's talk about our 3 parameters. First is size. Okay, so I have RAID 0 with n number of disks, and that's greater than or equal to 2 disks, right? You can't have RAID with a single disk. That makes no sense. It would just be a single disk. But with 2 or more disks, what do I get with the size? I get the storage capacity equals n times a single disk. This is very trivial, right? Disk 1, disk 2, disk 3, if those were all 1 terabyte disks, my storage capacity is now 3 terabytes. You see that? So size, I just multiply it times the number of disks in the array. Very easy. So I've tripled the size if I have a 3-disk array. What about performance? We have 2 categories, read and write. So let's look at them. When I'm writing, assuming my controller isn't the bottleneck or the thing that slows things down, assuming that the disk is the slowest part of the system, which is a reasonable assumption for most smaller arrays, what kind of write performance benefit do I get, or is there any? And an easy way to measure that or see that is to just ask the question, how much data, compared to the size of the original file, how much data actually has to be written to each disk? And we see that in the case of our 3-disk array, I write only 1/3 of the data at a time to each of 3 different disks. So basically, I could do these writes in parallel, couldn't I? I could write A to D1 while I'm writing B to D2 and C to D3. And in our tiny little example, we also have to come back and write again a second block to D1. But you can imagine that if we had lots and lots of blocks, let's say it's a very large file transfer, that it would average out to about 1/3 of the data going on each of the disks. Could be a little more for D1 and D2, depending upon how many blocks and where it ends, right, if it doesn't divide by 3 evenly. But if I had 20,000 blocks to write, you would say, okay, 1/3 of the data went to D1, 1/3 to D2, and 1/3 to D3. So that means since I'm writing 1/3 of the data, I can do it in 1/3 of the time, which means my performance, it's 3 times as fast, if you will, right? So basically, the write performance, I'm going to say n times, nx, okay? It is n times as fast, where n is the number of disks, greater than or equal to 2. 2 disks is twice as fast. 5 disks, it's 5 times as fast. With the read performance, notice too I can do these reads in parallel. I can read from disk 1 and disk 2 and disk 3 simultaneously. So it's the same thing. The performance in read, it's n times as fast. If I have 5 disks, it's 5 times as fast as a single disk if the disk controller and the system can otherwise keep up. So you see, I've multiplied my performance by n. I've multiplied my size times n. So the last question was reliability. Reliability. What have I done with my reliability? Well, here's the question. Let's compare it again to a single disk. If I have a certain likelihood that a disk is going to fail on a certain day, let's just assume that for one of our drives, the chance is 1 in 5,000 that it's going to fail today. If I have a whole box of them, is the likelihood that one of them is going to fail less or greater than if there's a single one? Well, the fact is that if I have 10 disks, I have 10 different chances for one of them to fail, right? I'm not looking for the chances that all of them fail. I only need one to fail to lose data. Do you see that? Look at our file again. Our file is A, B, C, and D. If any one of these disks goes down, if disk 2 goes down, I lose the data B. The data B doesn't exist anywhere else. There's no way I can get it back. That data's gone. And so therefore, my file is corrupt. So I've lost the file. If I have many files on these 3 disks, if one of the disks fails, I lose everything. None of the files has its integrity. None of the files has all of its data. And so all of the files are corrupt. And if I'm running a database server, of course, all of the data has gone down. So see, I've gotten size and performance, but I don't have any redundancy of information. So the question is this: is it more likely, if I have 3 disks, is it more likely one of them will fail than if I only had a single disk? And the answer is yes. It's much more likely because I have 3 chances to have a failure today instead of just 1 chance to have a failure. If it's 1 in 1,000, I have 1 in 1,000 that D1 is going to fail, 1 in 1,000 that D2 is going to fail, 1 in 1,000 that D3 is going to fail. Sounds like I have 3 chances in 1,000 that I'm going to have a failure today, which is bigger than 1 chance in 1,000. So reliability, it's lower. Reliability goes down compared to a single disk. So that's RAID 0. You get size and performance, certainly, but reliability goes down. Now, where would you use RAID 0? You could use RAID 0 in an application where performance is much more important than keeping the data. That is, where a data failure, for whatever reason, isn't going to be very costly. But you really need the data to be able to be written to or read from disk much faster. When are there applications like that? Now, I can think of a variety of applications, but they probably don't have a lot of application to databases. For instance, I can imagine in a video editing workstation. A RAID 0 array makes a lot of sense for a working drive and for a cache drive and for a place where intermediate video is being written to and read from. That makes a very fast solution. But in such a case, you don't put all of your footage on there and have that be the only place. Your video footage would be on different disks and would be on redundant storage somewhere, but you might use RAID 0 as a working drive to be able to make things go much faster. So there's an application, but not really necessarily a database application. And we would probably have to struggle pretty hard to find a good database application for RAID 0, but you need to be aware of it. The next one that we want to talk about is RAID level 1. So let's look at RAID level 1. RAID level 1 is also what we would call pure mirroring. And mirroring is just what it sounds like. You know what a mirror is, right? What is a mirror? A mirror is simply a flat surface that allows you to see, if there's an object here, you can see the reflection of the object in the mirror, right? Okay, so it's a metaphor for what RAID 1 does. What it does is it makes an exact copy of the data on more than one disk. Now that could be 2 drives or it could be more than 2 drives. So RAID 1 can certainly have more than 2 at a time. But let's consider the case where we have 2 drives, disk 1 and disk 2. And what we will do is write our file. Remember, it was A, B, C, D. And we're actually going to write the file to both of the disks so that the exact same data is on both disks. Okay? So let's look at what this does with respect to our 3 metrics. The first one, size. Compared to having a single disk, is the size less than, equal to, or greater than having a single disk? And the answer, of course, is it's the same, because you could just look at one of these disks and you see the whole data is on that disk, right? Or this one, the whole data is on that disk. So have I increased my capacity? Not at all. Neither have I decreased it, but I am using twice as many drives, right? So the size, no change. So I'll say 1x compared to just using a single disk. And once again, by the way, it doesn't have to be just 2 disks. I could have 3 disks. Why would I want to do that? Well, there are a couple of reasons, and that takes us to point number 2. Here's the first point. The second point, performance. Let's talk about write performance first. When we go and write the data, we're writing, in this case, this file is 4 blocks, right? What do you think? Same performance, faster performance, slower performance? Well, when I go to write block A, look what I have to do. I write block A to disk 1, I'm writing it to disk 2, and I'm writing it to disk 3. Now again, assuming that the controller is fast enough that it doesn't become the problem, okay? We're assuming that the disks are the slowest thing in the system, which is often a good assumption. I can write to these 3 disks that data for that block simultaneously, can't I? But it's the same block. I've only gotten 1 block through the file. The same thing with B, C, and D. I write B simultaneously to all 3 disks. So we write B simultaneously, and that takes as long as 1 block would on a single disk. Same with C, same with D. So it takes the same amount of time as if I had a single disk. It's not faster. And given the assumptions we've already made, it's not slower either. So I get no benefit. It's not faster. But what about the read performance? What about the read performance? What's interesting with the read performance is that I can use the disks in parallel, can't I? How would we do that? Well, I would read block A from disk 1 and at the same time read block B from disk 2 and at the same time read block C from disk 3. You see, I can read a different block from each of the disks in order to get my whole file. So as long as I'm reading a big file, let's say again, our file is actually not 4 blocks, but 20,000 blocks, you see that I would read about a third of the data from each of the disks, and I would be able to do that in parallel so that I would be able to read 3 times as fast. So if n is the number of disks, in this case n was 3, but n could be some number, it could be anything greater than or equal to 2, I'll say that the read performance is n times as fast. So you see I do get a performance benefit with RAID 1, but only in reads, not in writes. Very important distinction. Let's look at the third metric. The third metric is reliability. What is the reliability here compared to a single disk? Well, before, remember with RAID 0, losing any single disk would result in a failure of the whole array. The data is gone. It's not recoverable. And so having more disks actually reduced our reliability. But with RAID 1, it's a little different scenario because each of the disks has all of the same data. And so what happens in our example above if we were to lose disk 2? It fails. It stops spinning. The data cannot be recovered from disk 2. Have we actually lost our data? No, because the file, you see, still exists on disk 1 and disk 3. Now you will note that if we're reading that data with disk 2 having failed, that our read performance has gone down a little bit because we can no longer read from 3 drives in this case. We can only read from 2 simultaneously. So our read performance will degrade somewhat. The array will not be as fast in reads as it was before. But I still have all of the data. And so I haven't lost anything with one disk failure. What if another disk fails? Let's let disk 1 fail. Now I've had 2 failures. Do I still have all the data? Yes. The read performance has decreased again. Now, in fact, the read performance is the same as for a single disk because that's essentially what I have. I have a single disk. This one right here, right? Disk 3. That's all that's left. So now it's behaving like a single disk. Of course, if I lose disk 3, then I've lost my data. But I still haven't lost my data. I had 2 failures. So would you say this is more or less reliable than a single disk? Well, this is more reliable than a single disk because you see I have to have multiple failures. In fact, I have to have 3 failures in order to lose my data. So reliability, we're not talking about just the chance that a disk fails. We're talking about the chance that I lose data. That's what we mean by reliability. How likely am I to lose data in the case of a disk failure? And the answer is here, very unlikely, because I would have to have 3 disks fail before I was able to rebuild the array in order to lose data. So the reliability is much higher, much higher. In fact, I'm going to say highest. Of everything we will look at, the reliability of RAID 1 really is the highest. Okay, so let's talk about RAID level 5, which we will call striping with parity. I haven't used the vocabulary of striping before, but remember with a little aside here, with RAID 0, how we put the data on 2 different disks, 2 or more different disks, so that we had disk 1, disk 2, and etc., etc. Okay, however many blocks we have, we alternate blocks across 2 disks. Or if it were 3, then we would take 3 at a time, but we would alternate across the disks. This idea is called striping. Okay, this is striping. So now we're going to look at something different, which is striping with parity. This is RAID level 5. That was RAID 0. What does RAID level 5 look like? You need a minimum of 3 disks to do RAID level 5. And so let's set up just a simple scenario. Disk 1, disk 2, and disk 3. And this is a RAID 5 array. Okay? So with our 4 blocks that we had before, A, B, C, and D, we will write them to the disks like this. A goes to disk 1, B goes to disk 2, and disk 3 is going to get something, a function that we're going to calculate called parity. We'll say that it is the parity of A and B. That's what goes on disk 3. And I'll explain parity in a moment. And then we need to continue writing our file. We'll write C on disk 1. We're going to skip disk 2. We're going to write D on disk 3. And disk 2 gets parity of C and D. Now let's just pretend our file is a little bit bigger, has more blocks, so I can continue this procedure writing. Notice that the parity is on this disk, that it's on this disk. Where do you think it's going to be next? It's going to be down here. So let's say we'll write E and F right here, and disk 1 then gets the parity of E and F. I'll explain why we move the parity around from disk to disk. And if our file continued, it would be G and H here, and this would be parity of G and H, and etc. So you see the parity, we're alternating disks as we go. Okay? More on why we do that in a little bit. But back to our original file then. Remember, A, B, C, and D was all that we had. We have 3 disks. We've calculated this parity value. Now the parity is a very easy thing. One kind of parity, which is very common and very easy to understand, is a parity produced by using an exclusive OR operation. In fact, at this point I'm going to revisit the values that we had for A, B, C, and D in the beginning. Right? Remember these right here? Let's look at them. A is 0, 1, 0, 1, so let's write it down here. A is 0, 1, 0, 1. We have B, C, and D. Let me go get those values because I foolishly did not write them down anywhere except here. 0, 1, 1, 0 for B. 0, 1, 1, 0. C, we said, in our example, is going to be 1, 0, 0, 1. Okay. 1, 0, 0, 1, and a D was 1, 1, 1, 1. Okay. So the way that we're going to calculate parity is with an exclusive OR operation. So let's look at that. We have disk 1, disk 2, and disk 3, which of course has the parity for the first one. So A is 0, 1, 0, 1. B is 0, 1, 1, 0. And now we need to exclusive OR A and B. What do we get? We get 0, 0, 1, 1, don't we? So I'm going to go 0, 0, 1, 1. That's the parity. Now we need to write, according to what we said before, C goes right here. That's 1, 0, 0, 1. And D, remember we're going to skip to disk 3. So that's 1, 1, 1, 1. And so the exclusive OR of those two, C and D, is, of course, 0, 1, 1, 0. Okay? And that's the parity, isn't it? Now then, in normal operation, when we want to write to the disk then, we're sending the write to the controller, it's calculating the parity and it's deciding where to put the parity. And it knows which disk the parity is on for any set of blocks. But what about then when we're reading back? Well, once again, we ask the controller for blocks A, B, C, and D, and the controller knows that block A is stored here, that B is stored here, C is stored here, and D is stored here. So it reads it from the appropriate disks and ignores the parity data. But now let us consider what happens when one of the drive fails. Which one do we want to kill? We can really kill any of them, but how about we, let's say that disk 1 fails. Do we still have enough information to obtain all of the original blocks? When we go to read block A, remember block A was written here. We can't directly access that from disk 1 because disk 1 has failed. But there's an interesting property of exclusive OR such that I know that if I take this value and exclusive OR them together, I should get that value back out. So let's see if it works. I've got 0, 1, 1, 0, and 0, 0, 1, 1. And so I get 1, 0, 1, 0, like that. Okay? And so that is the value for A. You see that? So I was able to get A back even though the drive was lost, and A doesn't exist in any explicit form. It's built into the parity data and the data here for B. So I can get A, I can get B, can't I? Because B is just there. What about C? C is gone as well. Well, once again, I'll take this and this, 0, 1, 1, 0, and 1, 1, 1, 1, exclusive OR those 1, 0, 0, 1, and look at that. C equals 1, 0, 0, 1, so I'm able to get C from there. I'm able to read D from here, which is where D was stored. And so I can still get all of the data. Now notice that as I do that, instead of dividing the read duties for a large file across 3 disks, now I'm dividing it across 2 disks. And for 1/3 of my blocks, I have to calculate from all of the disks the value that I'm looking for. To recover this block, I have to consult every other disk in the array. And so my performance is going to go down substantially when I have a failure, but I can still get the data. So, just to be general, notice that I can have any number of disks in this RAID 5 array. Typical values for the number of disks in a RAID 5 array could range anywhere from a minimum of 3 up to as many as, say, 16 disks in the array. And that array can tolerate the failure of a single disk. But note, of course, that if I were to lose one of these other disks, obviously there's not enough information remaining for me to be able to get my file back. So a second failure is out of the question. 2 drives fail, RAID 5 fails. That's the way it works. But I can have some number of disks, let's call it n, and let's talk about then our 3 metrics. First, storage size. You can convince yourself very easily that we have increased the storage size compared to a single disk by a factor of n-1. So it's times n-1. So if all of these disks were 1 terabyte, then I would have n terabytes of total storage, but I use 1 disk, even though it's spread out, I use 1 disk worth of storage for parity, you see? So it's n-1 is the multiple. So in this case, where we had 3 disks, I get twice as much storage as a single disk. So I've got 1 disk worth of storage that's used for the parity values, even though they're spread out across the disks. Okay? So that's size. Notice, by the way, that this is more space efficient than RAID 1. Because in RAID 1, I have complete redundancy. For every data that I have to store, I use at least twice as much storage if I have one mirror. Whereas here, this is often called N+1 redundancy. Okay, I have one additional drive that I need to add. Second, performance. Consider, first of all, the write performance. When I was writing A, B, C, and D to my disks, notice that I'm able to spread out the writing across a large number of disks, but that I'm writing some additional data, which is parity data, right? And so the performance is higher, and it does scale, but it's not exactly linear in the number of disks. Consider that we're always writing the parity data to one disk, so we can ignore that in our calculation, and we're spreading out everything else amongst N-1 disks. So, write performance, if the disk is the slowest part of the system and there are no other bottlenecks, then it's N-1. And note that that is also the same for reads. It's faster by a ratio of N-1, where N is the number of disks. So if I have 3 disks, the reads and writes ought to be twice as fast as if I had just a single disk with no RAID. So you can imagine if I had an array with 16 disks, then theoretically that could be 15 times faster in reads and writes. That's a huge performance gain, but in reality, of course, there will be other bottlenecks in the system. And so you can't expect it to just continue to scale like that forever. The bus will not support that much data. The controller will not support that much data. But it is very common to have RAID arrays that these days approach the speed of several disks. And usually, if you look at the interface that you're using and the controller, you can determine kind of the performance sweet spot where maybe a 5-disk array or a 6-disk array or a 7-disk array will totally saturate the controller or the bus, and maybe that's a good spot to be aware of. Now the third thing, of course, is reliability. Reliability of RAID 5, let's say that it is high. Now remember, what did we say for RAID 1? We said RAID 1 highest. You know why? Because we've got completely redundant information. If I have n number of drives, I can have n-1 of them fail. As long as I still have one drive that's running, I've got all the data. But with RAID 5, I can have one failure, but I can't have more than one. If I have a 16-drive RAID 5 array and one drive fails, I'm fine, although my performance will decrease. But if I have a second failure, the array is dead. The other thing you want to consider with RAID 5 is, and we haven't really talked about it yet, but we want to talk about rebuilding a little bit. With RAID 1, rebuilding the array is really easy. What I mean by rebuilding is, if a drive fails, of course you don't want to just leave it like that. You'll replace it with a working drive, and then you want to rebuild the array. With RAID 1, the rebuild is fairly straightforward. We want to copy one of the other disks in the array to the failed disk. Now if I have a 2-drive array, so that I've got drive 1 and drive 2, I have a new drive 1, which is, let's say drive 1 was the one that failed before, so I have a new one that's empty, and I have drive 2 that has A, B, C, and D. Now this is, we're talking about right here, RAID 1, okay? if this is my scenario, drive 1 failed before, so I replaced it with a new empty drive. What do I have to do? I have to copy all of this to drive 1. And if these are big drives, let's say these are 4 terabyte drives, this can take a little time. And if in the meantime I am operating this drive, I'm still writing to the drive, and I'm still reading from the drive because my database is still up and running, I'm putting a big burden on this drive to also copy the data off. But until it's copied, if I had just a 2-drive RAID 1 array, until it's copied, I'm very vulnerable, aren't I? Because if drive 2 fails, then I'm in real trouble. All my data is gone, and there is no reading and writing anymore to drive 2. Okay? So I have to rebuild the array, and that takes some time. Now, if on the other hand, I had multiple drives, multiple mirrors, then I can spread those copy operations out across the drives, and that's very helpful. But now let's look at a RAID 5 rebuild. I've got drive 1, let's say that was the one that failed, so it's empty. Okay, and I've got drive 2, drive 3. Let's just make another drive. We'll say this is a 4-drive RAID 5 array. Okay, and so maybe this has B and C and the parity of A, B, C. And maybe, let's see, that would have put D right there, and E would be right here. And this would be F, and this would be the parity of D, E, F, etc. Okay? And so what do we need to do? Well, obviously we need to write A over here, and we need to write D over here. How are we going to get them? Well, we have to calculate A using the data from B, C, and the parity. Okay, so all 3 of these have to be read in order to produce A. I have to read a block for each one. And I have to use all 3 of these, remember, to recover D and then write it out. So the number of block reads and the calculations involved are very expensive. So this process is slow. And because it is slow, there is an opportunity that one of the other drives fails. Not only that, keep in mind that this whole array, in the meantime, we are still running. So we have reads and writes. Our normal database activity is going on. The performance has gone down, we're still doing the normal stuff, and we're trying to rebuild at the same time. So we're really hitting these drives very hard. This is one of the problems with RAID 5, is what happens after a drive goes down. If you've got a fairly loaded system, it can become very unreliable or very risky during the rebuild process. That's a time when you hold your breath and you hope that everything comes out okay. So we'll talk about a way to mitigate that a little as we turn to RAID 6. But let's understand the challenge here. We could, during a rebuild, what if a rebuild fails? And how can it fail? One is we could have another drive fail. So the first possibility is a second drive failure, okay? And by that we mean a total failure. The second thing that could happen is what we call the unrecoverable read error. The unrecoverable read error, or URE. And we've spent a little bit of time in class talking about this already, so I'm not going to spend a lot of time on it here. You had a homework problem on UREs and what they mean during a rebuild. But understand that most hard drives will tell you that you will have one URE in 10 to the 15 to 10 to the 14 reads. This value depends. This is kind of for consumer drives. Most enterprise drives claim a 10 to the 15. In other words, for every bit, this means that there is a bit that has been successfully written to the disk, but that for whatever reason is no longer able to be read with any accuracy. In other words, a bit flips or has a non-deterministic value so that it can go either way. This can happen because of defects in the media. It can happen because of some physical thing. For example, one stray X-ray particle carries some, one stray bit of radiation carries some energy with it and changes what was stored in a bit position. But for whatever reason, in about that many bits, somewhere in this order of magnitude, number of bits, you're going to have an error where the bit is read the wrong way or is unreliable. Okay, so you really don't know what data was stored there unless you have it in some redundant form. So what that means is the integrity of your file has been violated in such a case. And it turns out, if you do the math, you look at 10 to the 15 to 10 to the 14 bits, you're talking about on the order of a few terabytes of data, okay? A few terabytes of data. Every few terabytes, you're going to have a URE. Now the problem is, back when we had hard drives that were 50 gigabytes, UREs weren't a big problem during rebuilds because they occurred very rarely. But now that we have a URE every few terabytes and we have drives that are a few terabytes, your likelihood of having a URE during a rebuild is very high. So you've lost one of your disks. You put an empty in place, D1 here, right? And we're going through this slow process, and we're having to read all of the data off of all of the disks. They're multi-terabyte disks, and boom, we have a URE right here on disk 3. What happens? Can we recover that bit that's been erroneously read? No, we cannot. We cannot get it back. We have an unrecoverable disk error. The file's integrity has been violated. If you're running a database server, the database's integrity has been violated, and therefore you don't know what your data was. That is the same as if you lost the entire array, really, in most applications. If you're running a bank database, that might have changed. One bit could have doubled someone's bank balance, right? One bit error could double their bank balance. These are non-trivial things. So you've lost the integrity of your database. So what do we do to mitigate that? The main tool that we have available to us in just the simple RAID levels is RAID level 6. RAID level 6 is just like RAID 5, except we're going to keep twice as much parity data in the array. That means we need a minimum of 4 disks. So let's look at the case where we have 4 disks. Disk 1, disk 2, disk 3, and disk 4. And the way we will do it is we will store block A here, block B here. This will be a parity value calculated on A and B. And this will be another parity value that we'll call Q, calculated on A and B. Okay, so we have and then of course we want to write C here, and we'll write D way over here, and we'll make this the parity of C and D, and this will be the second parity Q of C and D. Okay, so I don't want to get into how these parity calculations work in RAID 6. It's a little more complicated than just the simple exclusive OR thing, and I was reading up on this a little bit, and it gets into finite fields and other discrete math topics. So it's really beyond the scope of what we're interested in here. But suffice it to say that what RAID 6 adds is the ability to recover the data with up to 2 drive failures. So we could consider perhaps, let's say that we lose drive 1 and we lose drive 2. Both of them are down. Now you'll notice that all that we have left are the 2 parity values for A and B, and we have the parity value for C and D, and then we just have, that's the only actual data, of our original data that's actually existing in any form. But we can, from these 2 parity values, we can calculate from these 2, we can calculate A and B, and from these 2, we can calculate C, and of course we have D. So we can recover our file. Once again, the controller will continue to allow the array to operate in this situation with just, in our case, 2 disks running, but the performance will be degraded considerably. And a rebuild with 2 failures in RAID 6 similarly will be very slow. In fact, because these calculations may be a little more complex, it might even be take a little longer than a RAID 5 rebuild. And in the meantime, the disks are still operating. But the case of 2 failures is kind of your not as common case. The more common case is 1 failure. And in the case of 1 failure, while you're doing the rebuild, you have some safety. If you encounter a URE during the rebuild, you can still get the data. And you can get past that, and then you can remap the bad sector. And the controller will do this for you. Remap the bad sector where the URE occurred and keep going. So RAID 6 is much more reliable than RAID 5. Is it as reliable as mirroring? No, because you still can't necessarily tolerate as many failures. For example, if I have RAID level 6 with six disks, as in this case, I can tolerate 2 failures, but on the 3rd failure, the whole array is gone, right? But with RAID level 1, I have mirroring. All I need is 1 disk to still exist, and I still have the data. So let's talk through them real quick. 1, space is pretty easy. It's times n minus 2, where n is the number of disks. Same thing with performance. In both reads and writes, just like in RAID 5, but it's times n minus 2. And now in reliability, you have, it's more reliable than RAID 5, less reliable than RAID 0. What about compared to a single disk? Well, with a single disk, 1 failure, and you're done. With RAID 6, it takes 3 failures, actually, before you're done. 2 failures, you can still run. So it has greater reliability than a single disk, right? Okay. I did mention that I wanted to say where we're doing parity calculations, why we move the parity calculation from one disk to another. Instead of just having one drive that's all parity data, why do we, going back to our drawing here from above, why do we do this? Why do we put the parity data across the drives like this, so that instead of putting it all on disk 3, we put some here, some here, some here? And the answer is very simply to spread the load out in terms of the parity data, because no matter what else we're doing or what blocks we're reading, or what blocks we're writing, we are always having to update the parity data and perform writes to the media. And by spreading the parity data out across the drives, we spread the workload. So that's it. Okay, very quickly, I just want to talk a little bit about some of the hybrid RAID levels, so you know what those are, and then we will be finished here. The hybrid levels combine different RAID levels in order to get some of the benefits of both. And the first one I want to tell you about is called RAID 0 plus 1. It's very simple. We're going to have a RAID 0 array, and we'll call it A. And then we're going to have A prime, which is an exact mirror of it. It's a RAID 0 array. Now remember, RAID 0, high performance but low reliability. So why don't we have two of them that have exactly the same data? And that way, if one of them fails, we still have the other one. And we get the performance benefits and the size benefits of RAID 0. So since we're calling that a mirror, right, we'll draw it like this. So this is a RAID 1 array of RAID 0 arrays. Does that make sense? This is RAID 0 plus 1. You get the redundancy of RAID 1, at least part of it, right, with the performance of RAID 0 combined. Very nice. That's not the only way you can do it. You could do it the other way. This is called RAID 10, also known as RAID 1 plus 0. What do you think is going to happen here? You guessed it. RAID 1 array here, RAID 1 array here. They are combined as a RAID 0 array. So what do we get? We've got multiple disks here that are mirrors, right, of each other. Okay, these are mirrors, and they are striped by a RAID as a RAID 0 array for performance purposes. So remember, when we're writing to the RAID 1 array, we have to write, since they're mirrors, we have to write to all three. Here, then, we're going to get, in this case with two RAID 1 arrays, we're going to get double the write performance here. And of course, with RAID 1, our read performance is already multiplied by the number of disks. Same here, right? So I could draw it like this, couldn't I? 4, 5, 6, something like that. So I get the benefits of RAID 0. Basically, I've increased my write performance by doing this. Now, what happens if I have a failure here? Boom, that disk goes down. Well, remember, this is mirrored, so I haven't lost anything except a little bit of performance here. All right? And I can have a failure here and a failure here, and I'm still up and running at this point. If I have another failure, of course, that RAID 1 array has failed, which means that's gone and that's gone. Okay? But you see how that works. That's not the only way we can combine different RAID levels. RAID 50, otherwise known as 5 plus 0. Now remember, anytime we're looking at the RAID levels, the first number is the number that's kind of at the bottom of the hierarchy. So this is a RAID 5 array. Let's draw it this way. We'll make 3 RAID 5 arrays here. Okay? And we have a RAID 0 array now of these RAID 5s. Okay? Again, why would we do that? Because this has 3 times the write performance and 3 times the read performance of any of those RAID 5 arrays by themselves. Each of these has at least 3 disks, right? And those 3 disks, I can tolerate a failure of any one of them and still get the data, and I've got 2 times the storage, right? Because I've got 2 plus 1 parity. Or it could be 8 plus 1 parity, and I have 9 disks, whatever it is, okay? Okay. Last one, of course, and I probably don't even need to draw it, but I'll do it just for completeness. RAID 60, which is 6 plus 0. Again, this is a RAID 0 array of RAID 6 arrays. We'll just put 2 of them in the drawing this time. Okay, so the data, I've got 2 RAID 6 arrays here with all of the benefits of RAID 6. Remember, we have at least 4 drives in here. I can tolerate the failure of 2 drives and still continue running, so I've got a lot of fault tolerance here. But I've now striped the data block-wise across these 2 so that I can get increased performance. in reads and writes. That is it. That is the end of our discussion. But I am going to create a table here so that we summarize everything that we've looked at. We've got RAID 0, RAID 1, RAID 5, RAID 6, and then the single disk. And I won't bother doing it with the compound RAID levels, but it's there if you want it. So we want to know how many disks does it take? What's the capacity? That's our storage metric, right? Reliability, and the speed or performance for writes and for reads. So let's look at it. For RAID 0, how many disks does it take? 2 or more. The capacity, if you have n number of disks, it's times n, right? Reliability, low reliability. The write performance times n, the read performance times n. What about RAID 1? How many disks? 2 or more disks. The capacity is just 1 times a single disk. See, I should have put single first. In fact, I'll go ahead and do it. Number of disks for a single disk, of course, 1. The capacity times 1. Reliability, we call this the average or nominal. That's where we're starting, right? Because that's what we're comparing against. The speed in writes times 1 and in reads times 1. Okay, so that's our comparison. So with RAID 1, 2 or more disks, the capacity is the same as a single disk, no matter how many you have. Reliability is really good. The speed in writes times 1, remember, because we're writing all the data to each one. In reads, it's times n, because we can divide by blocks. RAID 5 takes 3 or more disks. The capacity is times n minus 1. The reliability here is, we'll call it, I don't know what we should call it. We called RAID 1 good. I'm going to change that to very good. Okay, so that way we can call this good. All right. The write speed times n minus 1. The read speed times n minus 1. Okay. RAID 6, you know it takes 4 or more disks because you have to have 2 for parity. The capacity, it's times n minus 2. Reliability for RAID 6 is also very good. And how do I compare that to RAID 1? It really depends upon how many disks you're talking about. Because if I have RAID 1 mirroring with 5 disks, that means I could tolerate 4 failures. If I have RAID 1 mirroring with 1 disk, it means I can tolerate 1 failure. RAID 6 can always tolerate 2 failures. So see, RAID 1 could be more or less reliable than RAID 6. It depends upon how many mirrors you have. If you have 1 mirror on RAID 1, RAID 6 may be more reliable. But then my chances of having multiple disk failures increases as the number of disks increases. If I have 20 disks in my RAID 6 array, then my reliability goes down compared to if I just had 4. So we're just going to call them both very good. The speed in reads and writes, you know what it is, times n minus 2. And there you have it. That's the end of our discussion. I'm sorry it was so long, but you need this as you go out into the field and consider implementing solutions. You need to know something about the physical storage. And so hopefully this has been a help in that area.